AMPOT, Monitoring and Defending Against Amplification DDoS Attacks by Sada Lamari. The beginning, denial of service (DOS) attack is an attempt to make a machine or network resource unavailable to its intended users, such as to temporarily or indefinitely interrupt or suspend services of a host connected to the Internet. Denial of service is typically accomplished by flooding the targeted machine or resource with superfluous requests in an attempt to overload systems and prevent some or all legitimate requests from being fulfilled. A distributed denial of service (DDoS) is where the attack source is more than one, often thousands of, unique IP addresses. It is analogous to a group of people crowding the entry door or gate to a shop or business, and not letting legitimate parties enter into the shop or business, disrupting normal operations. The scale of DDoS attacks has continued to rise over recent years, even reaching over 400 gigabits per second. Criminal perpetrators of DOS and DDoS attacks often target sites or services hosted on high-profile web servers such as banks, credit card payment gateways. Motives of revenge, blackmail or activism can be behind other attacks. A domain name server (DNS) amplification attack is a popular form of distributed denial of service (DDoS), in which attackers use publicly accessible open DNS servers to flood a target system with DNS response traffic. The primary technique consists of an attacker sending a DNS name lookup request to an open DNS server with the source address spoofed to be the target's address. When the DNS server sends the DNS record response, it is sent instead to the target. Attackers will typically submit a request for as much zone information as possible to maximize the amplification effect. In most attacks of this type observed by USCERT, the spoofed queries sent by the attacker are of the type I grave envoy, I circumflex, which returns all known information about a DNS zone in a single request. Because the size of the response is considerably larger than the request, the attacker is able to increase the amount of traffic directed at the victim. By leveraging a botnet to produce a large number of spoofed DNS queries, an attacker can create an immense amount of traffic with little effort. Additionally, because the responses are legitimate data coming from valid servers, it is extremely difficult to prevent these types of attacks. While the attacks are difficult to stop, network operators can apply several possible mitigation strategies. While the most common form of this attack that USCERT has observed involves DNS servers configured to allow unrestricted recursive resolution for any client on the Internet, attacks can also involve authoritative name servers that do not provide recursive resolution. The attack method is similar to open recursive resolvers, but is more difficult to mitigate since even a server configured with best practices can still be used in an attack. In the case of authoritative servers, mitigation should focus on using response rate limiting to restrict the amount of traffic. The impacting misconfigured domain name system (DNS) server can be exploited to participate in a distributed denial of service (DDoS) attack. For the solution is by detection, that we discuss in the next slide. AMPOT, our novel honeypot that monitors amplification DDoS attacks. The background. We have discussed it in slide before, but for the reminder, I will explain again a little. Amplification DDoS attacks aim to congest the network bandwidth of attack targets. Attackers use two main techniques to launch amplification attacks. First, They abuse UDP-based internet services that reflect traffic. For example, attackers may abuse open DNS resolvers to trigger responses to DNS lookups. By choosing particular DNS queries, attackers can even ensure that the responses are much larger than the requests, therefore, triggering traffic amplification. Second, attackers spoof the source IP address of the traffic so that the responses flood the victim, instead of going back to the attacker. Such attacks inherently require amplifiers, hosts offering services that are vulnerable to amplification (DDoS). For many of these protocols, adversaries simply use internet-wide scans to identify millions of amplifiers. Once discovered, attackers will abuse a subset of the discovered amplifiers as part of their attacks. Honeypot design. In the following, we will describe AmpPot, which acts as a fake amplifier. Based on the above observations, we can use this honeypot to the first monitor reconnaissance steps performed by potential attackers, and the second monitor amplification attacks. AmpPot mimics services having amplification attack vectors by listening on UDP ports that are likely to be abused. In particular, AmpPot supports all protocols that are said to be vulnerable for QOTD 17, ChargeN 19, DNS 53, NTP 123, NetBIOS 137, SNMP 161 and SSDP 1900, plus MSSQL 1434 and SIP 5060-5061. To serve these protocols, AmpPot listens on the according ports for incoming UDP packets. Modes. Whenever AmpPot receives a request, it will respond. We use 3 modes that influence the type of response we send back. Emulated. In this mode, we use protocol-specific parsers. If a request is valid, we reply with a response, which is randomly chosen from a pre-generated set of protocol-specific responses. For a few protocols such as DNS, which requires dynamically generated responses that are specific to the request, the query domain name, we recursively resolve the requested resource before responding. Proxied. The proxy mode turns AmpPot into a proxy that forwards requests to internal servers that actually operate the vulnerable protocol. The responses, in turn, are sent back to the client. While this mode requires configuring servers, such as a DNS resolver or NTP time server, it has the advantage that no emulation is needed. Agnostic. Finally, when run in the agnostic mode, AmpPot responds regardless of the validity of the request. In fact, even the response is invalid. AmpPot replies with a large response that contains random bytes, either 100x the size of the requests, or with the maximum MTU. This mode assumes that the attacker does not really care about the validity of the responses, but instead just aims to find hosts that send back large replies. Responses. AmpPot is most attractive for attackers if its responses result in amplification. To be attractive, we carefully design protocol-specific responses, emulated mode or configured servers that send back attractive payloads, proxy mode. For example, for DNS we resolve the request that the client sent, and respond with the entire response, in particular also following the DNS extensions to support large payloads. Furthermore, we trigger responses that are both vulnerable to NTP as monist request and many other amplifying responses. We gained this knowledge by A. Inspecting known vulnerability reports, B. Passively observing requests targeting a dark net. C. Scanning the internet to find typical large responses. Except for the agnostic mode, we made sure that popular client software for each protocol can successfully parse the responses. Rate limiting. By mimicking services that have amplification vulnerabilities, AmpBot runs a risk of becoming involved in actual DDoS attacks. On the other hand, in order to attract attackers, the honeypots need to respond as if they were vulnerable. We have thus added a rate-limiting mechanism to AmpBot that helps to distinguish between scans, to which we would like to reply, and attacks, in which we do not want to participate. In particular, we block a client IP address and its corresponding 24 networks if the client sends more than 10 requests per minute. Once a network is blocked, no requests from this network range will be answered. Data collection. One of the core components of AmpBot is data collection. We collect data in two ways: raw requests and filtered data. However, as the raw data becomes large and difficult to handle quickly, we also record a filter data set. Tool sharing. AmpBot is implemented in Python and follows a modular design. We will share AmpBot with trusted parties and make it accessible to fellow researchers, assuming that we can use the derived data as input for the attack portal. We deployed 21 AmpBot instances to collect attacker information. Most honeypots were deployed in 2014 and have been continuously operated since then. Table 1 summarizes our farm: 11 emulated, 7 proxying and 3 agnostic honeypots. The emulated honeypots are scattered across countries, whereas the other honeypots are all located at Japanese ISPs. In an attempt to make the honeypots popular, we try to host the honeypots at ISPs providing static IP addresses. In a few cases, the honeypots have semi-dynamic IP addresses. That is, the addresses change every 3-10 weeks on average, as indicated by the braces in the IP address column. The honeypots support a variety of protocols. The proxy honeypots support CHARGEN, QOTD, DNS, NTP, SNMP and SSDP. In a continuous effort to support more protocols, we gradually added SNMP and SSDP after an initial deployment with the remaining subset of 4 protocols only. PO2 support DNS only. The emulated honeypots support 3 additional protocols: NetBIOS, MSSQL, SIP. Finally, 2 of the agnostic honeypots listened on all UDP ports with varying response strategy settings. Agnostic F denotes that a honeypot always replied with 1472 bytes UDP payload. In contrast, Agnostic M multiplies the length of the request payload by 100 to create a response that is relative in length to the request. Either way, the responses contained random UDP payload that is not valid for the scan protocol. We define an attack, then give an overview of attacks, and finally analyze the attacks in more detail. Attack definition, attack overview, honeypot convergence, deployment to abuse. Attack sources, attack duration and repetition, victim analysis, request entropy. Attack definition. We aggregate attacks based on the source IP address, the attack victim and destination port, the protocol being abused. We group attacks seen by multiple honeypots into one combined attack, as long as the source IP address and the abused protocol match. If an attack pauses for an hour, and then resumes, we separate the traffic into 2 attacks. Attack overview summarizes the attacks our honeypots monitored over the period. Honeypot convergence Did we deploy succinctly many honeypots to detect all attacks? We aim to answer the question of which honeypot mode was most elective. To this end, we drew convergence graphs with swapped orders of the honeypot modes, one with proxy honeypots first, and one with agnostic honeypots first. The share of attacks that are missed by the agnostic honeypots is significant, meaning that not all attackers blindly accept any large response. While this shows that agnostic honeypots alone are not sufficient for complete analysis, they are still helpful to capture new attacks, not only those abusing previously unseen protocols. We speculate that some attackers may favor the agnostic responses, as they are sometimes even larger than proxied or emulated responses. A good rule of thumb is to run agnostic honeypots in parallel to others. Deployment to abuse. We analyze the time span between deploying a honeypot and the time it gets abused. In fact, all honeypots were already abused within 24 hours after deployment. However, the number of initial attacks was quite low, and we saw an increasing number of attacks as days passed after deployment. On average, the attacks observed at the honeypots reach a steady level after 5 days. Attack sources are amplification DDoS attacks caused by single sources, such as booter services, or do multiple hosts cause an attack, such as DDoS botnets. We aim to approach the analysis by leveraging the time to live (TTL) field in the IP header. Generally, the TTL field is decremented by every hop that forwards an IP packet. For the following analysis, we leverage the fact that our honeypots would observe varying TTL values for an attack if multiple attack sources are used. In contrast, if there is a single source, we would see a fixed, or at most a few, TTL values, assuming that the route from attacker to amplifier does not frequently change, and assuming that the initial TTL value is not randomized. Attack duration and repetition. Our honeypots also reveal how long a victim is being attacked. For these analyses, we were interested in the victim, rather than the protocol used to attack the victim. Therefore, we have grouped the attacks by source IP address, and regarded attacks abusing multiple protocols towards the same victim as a single combined attacks. Victim analysis. In attempt to understand the motivation of the attacks, we inspected the targets of the amplification attacks. Request entropy. How much variety we see in the request of payloads. In an attempt to understand the attack techniques, we next inspected how much variety we see in the request payloads. Conc amplification attacks continue to be a dangerous threat to millions of users. We have shown that one can passively monitor attacks, and insights into these attacks can help to derive helpful Lucian countermeasures. However, our research has also identified new research directions, such as trying to understand the attacker's motives and actual origins. We have shown that DDoS botnets are likely not the main source for amplification attacks, shifting focus to other potential attack sources such as booter services. AmpBot assists in analyzing the amplification threats in more detail, and the web portal can help operational security operators to become informed about or to defend against attacks.